Well, welcome everyone. As you heard, I'm Olivia, and I'm so excited to be introducing our talk today on how to build an Earth, just add water. So we are Science in the News from Yale Science Communication, an organization of grad students at Yale committed to engaging in informative science outreach. So you'll be hearing from three speakers today about the origins of life on Earth and what makes it unique. Each of our speakers is going to speak for 15 minutes, and then we'll have time for questions at the end. So to meet our speakers today, first we have Garrett, who researches planetary system formation in the astronomy department. He's also a huge baseball fan who's visited 23 MLB stadiums. Next, we'll hear from Victor, who studies neurodegenerative genetic diseases and is from the garlic capital of the world. And finally, we'll hear from Dan, who models the behavior of water molecules in the molecular biophysics and biochemistry department. And like many of us this year, he's been getting into baking and has a sourdough starter named Evangeline. So before I hand things over to our first speaker, I want to give you a brief overview of our topic today. The goal of today's presentation is to give you a deep dive into how our planet became the Earth, this bright blue marble that you can see in the background here, that's capable of sustaining all of us. We sometimes take the existence of the Earth for granted, but the fact that the Earth was capable of creating and sustaining life is so incredibly unlikely that, as far as we know, it's never happened again. So first, Garrett is going to talk to us about the very beginnings of the Earth, the creation of the solar system, and where the first water on Earth came from. And then Victor is going to take us to the primordial Earth and show us where the first building blocks of life came from and why water was so important to their creation. And then finally, Dan will talk to us about the ways life on Earth is unique right now and how the asymmetry of the molecules of life are so important. So with that, I will turn things over to Garrett, our first speaker.
Cool. Thank you for the introduction, Olivia. Can everybody see my slides now? And if I go full screen, everyone can still see them. Okay, awesome. So as Olivia said, my name is Garrett Levine, and I'm a grad student here at Yale, and I study planetary astrophysics. So I study how do planets form and how does physics dictate how they change over time. So today I'm going to be answering the question of how Earth got its water. Now, let's motivate our discussion of water in the first place and why it's so important for life on Earth. And I think the best way to do this is actually to take a look at the Earthrise photo taken by the Apollo 8 astronauts. In front of you, you can see kind of the gray, dead, lifeless moon. And in the background, you can see this blue, dynamic, living marble, the Earth. And the thing that really differentiates the two of them is that the Earth has water and the moon does not. In fact, all life as we know it requires water. Pretty much everywhere on Earth we find water, we find life, and vice versa. So clearly there's some deep connection between the two. Now, to give you a sense of just how much water, or actually how little water we're talking about, I'm showing a picture on the left side as if you took all of the water in the Earth's oceans, balled it up into a sphere, and put it next to the dried out Earth. Now, as you can see, there's actually not that much water, but it is very important for life. And this leaves us with two ways of how the Earth could have gotten its water. First, the Earth could have been born with its water. Whatever stuff the Earth formed from could have had that sphere of water embedded in it, and that's how the Earth got its water. Alternatively, if this wasn't the case, Earth would have had to have acquired its water later. So let's dive into the science and see which one it is. Now, all good science typically starts out with observations. So what I want to do first is point out some interesting things about the solar system. Now, you've probably seen this cartoon figure of the solar system, but what I want to show you is a bird's eye view. This is essentially what you would see if you took a spaceship and looked down on the solar system. Now, there's some key observations that we can make here that will show us some patterns to how things formed. First, similar planets are grouped together. So we have the rocky planets all very close to the sun, Mercury, Venus, Earth, and Mars. Moving a little bit further out, we have the gas giants, Jupiter and Saturn. And moving even further out, we have Uranus and Neptune, the ice giants. So similar planets are made of similar things and they seem to be grouped together. Besides this, the solar system is actually about as flat as a pancake. So it's not really a hockey puck, but it's not a sphere. It's really this pancake-like shape. And finally, all of the planets actually orbit in the same direction. So this is suggesting some kind of a common origin. This is suggesting that all of the planets formed at the same time, and there's some pattern to how it happened. So around the year 1800, physicists actually started to piece together the puzzle, and they started to come up with this story that today we call the nebular hypothesis. So we'll get to why this is true in a bit, but first I just want to lay out the story itself. So let's imagine that somewhere in outer space, there's a cloud of gas and dust, and there happens to be so much matter, so much gas and dust, that the force of gravity actually attracts everything else in this cloud, and the cloud starts to collapse and it starts to shrink. Now, as this cloud starts to shrink, the gas and dust will actually spin faster and flatten into a disk. And at the center, where the most stuff is, there's a star, the sun is born. Now, with a little bit more time, the dust should stick together and form pebbles within this disk. These pebbles stick together and form boulders, and eventually these boulders stick together and they form planets. And we think that this happens on the time scale of a few million years. Now, this is a cool story, but we should actually try and figure out if it's true, and if so, why it's true. So I want to give you a little bit of intuition for how this might happen, and we'll try to make some connections to everyday life. So this cloud of gravitating gas, this gas that is, there's so much stuff that it shrinks itself down, will start to spin. And we can think about this like the ice skater in the animation here. So as she wants to jump and spin really quickly, she actually pulls her arms towards herself, and this allows her to speed up her rotation rate. She spins more quickly. Now, if we imagine this process playing out in this cloud of gas and dust that forms the planets, we can see why that cloud should also start to spin. Now, as this cloud spins, it should also flatten. So I like to think of this like the ride at the fair with the swinging chairs. When the ride first starts, all of the chairs are hanging straight down. But as the ride starts to spin faster and faster, the chairs rise. And we can imagine that if this fair ride got really out of hand, the chairs would completely flatten and they would form a disk. Now, again, we have much larger scales in outer space. Things spin much faster and they flatten into this pancake-like disk. So the key point here is that we can use the physics of everyday life to understand that this gravitating gas and dust cloud should form a protoplanetary disk. Proto meaning before, planetary meaning planets. So this is the before planets disk. Now, 200 years have passed since this theory was first developed, and in that time, we have computers that can perform really powerful simulations that allow us to get a more detailed look at the physics. So what I'm showing on the left here is actually the output of one of these simulations, where we have a cloud of gas and dust starting to collapse in on itself. Now, we've simulated for about 100,000 years, but if we fast forward for around 250,000 more years and we zoom in on a little patch of this, what we actually see is we see a disk starting to form at the bottom right of the screen. Now, this is really actually very remarkable because we haven't told the computer about ice skaters or fair rides or even disks for that matter. All we have told the computer about is that this gas and dust exists and that the force of gravity exists, and that's it. Yet we still recover the same behavior that we see in ice skaters and fair rides. We recover the disk structures that we actually predicted. So to me, this is pretty amazing. Now, again, in science, we really like proof. The computer simulation is suggestive that what we're thinking is on the right lines, but we really want observations to back it up. So the people that developed the nebular hypothesis actually figured out by looking up in the sky that they could see these clouds themselves. So I'm showing the Milky Way, and you can see the bright background stars, but in front of those stars, you can see these dark patches. Now, these dark patches are actually the clouds that form stars. These are the clouds of gas and dust. And once people came up with the nebular hypothesis, they put two and two together and figured out what they were. Now, with better and better telescopes, we can actually zoom in on some of these patches here, and we can see the really small clouds that form the disks themselves. This kind of corresponds to the second slide of our computer simulation. And what we see here is we see essentially a black cloud that there's so much gas and dust that it blocks out the stars behind it. There's no starlight getting through. So it's obviously really hard to see exactly what's going on in here. But again, with more and more powerful telescopes, we've actually been able to do so. So we found the clouds, and it's actually only within the last five to 10 years that we've started to find the disks. What we've done is we've developed telescopes that actually image the dust inside these clouds. And what we see is really remarkable. We see on the scale of around 250 Earth-Sun distances, which is about the size of our solar system, we see these disks starting to form. We see bright glowing dust, but what we also see is we see gaps in the disks. And these gaps are where the dust isn't. Now, you could hypothesize that within these gaps, this is where the dust forms pebbles, which forms boulders, which forms planets. And again, with even better telescopes, we've been able to look into the gaps of the disks themselves. So this is a bunch of images that were taken over different points in time. And what we can see is actually something moving in the disk, something really bright. And that is indisputably a planet. Now, this is the slam dunk for the nebular hypothesis. This is telling us this is how the planets formed. And it's quite remarkable that we can go from just an idea of what happens to this cloud of collapsing gas and dust, and 200 years later, have the computer simulations and the observations to back us up. So we've actually taken quite a detour from the water question, but now that we understand how planets form, we can think about what the conditions might have looked like when the Earth was forming. To do so, I want to take us from a bird's eye view, which is like looking at the disk from above, to an edge-on view, which is like looking at this stack of pancakes from the side. What I've done now is drawn this same cartoon diagram of the solar system, but I've shown what the disk should look like. And we should think about what the temperature specifically should look like within the disk. When we're closer to the sun, it's warmer, and moving further out, it gets colder. And at some point in this disk, there should be what's called the ice line. When I'm closer to the sun than the ice line, it should be hot enough that water boils away. It's a vapor, it's a gas. But if I'm further from the sun, water should be a solid, it should be an ice, it should stick to the forming planets. And you might ask where the liquid water is. Well, in outer space, water actually behaves kind of like dry ice does on the Earth. It goes from a vapor, from a gas, to ice and vice versa. There's no liquid phase because there's no atmosphere to support it. So we can get a sense of where this ice line should be by looking at objects in the solar system. For example, in the inner solar system, we have Mercury, which has no water. It formed too hot to have water. But moving further out, we see objects like Saturn's moon Enceladus, which is totally covered in ice. So somewhere in there is the ice line. And with temperature calculations, we can actually figure out that the Earth would have been too hot initially to form water. So the key point here is that water actually could not have been frozen in the material making Earth. It would have been a gas, and it wouldn't have stuck to these dust grains and these pebbles and these boulders forming the Earth. So the Earth has to have gotten its water somewhere else. To think about this, we actually need to turn our attention to the water molecule itself. You might be familiar with H2O. telling us that there are 2 hydrogens and 1 oxygen in a water. But what you might not know is that hydrogen comes in 2 main forms. It comes in what we would call regular hydrogen and heavy hydrogen. And what's interesting is that we can actually use the regular and heavy hydrogen as a way of telling where our water came from. If I look at Earth's water and I see a certain amount of heavy hydrogen, and I go somewhere else in the solar system and I see that same amount of heavy hydrogen, that's essentially a chemical fingerprint in a sense. That's telling us where our water should come from. So what I want to do is essentially match up the Earth's heavy versus regular hydrogen with something else in the solar system that has water, and that should tell us where Earth's water came from. So what I'm going to do on this slide is plot the same cartoon figure of the solar system we've been looking at, but the higher up on the slide something is, the more heavy hydrogen it has. So we actually see that the sun and the giant planets have around the same amount of heavy versus regular hydrogen. And this is good. This tells us that the nebular hypothesis is probably correct. They probably formed from the same stuff, so they should have similar heavy and light hydrogen. The sun also has about the same heavy hydrogen as our neighboring stars, which is also good because that tells us that the sun probably formed from the same stuff as other stars. The same types of disks that formed around these stars that we see probably formed around the sun when the sun was very young as well. Now, comets have too much heavy hydrogen compared to Earth, but Earth has almost the same proportion of heavy hydrogen as asteroids. So what this is pointing to is the Earth forming dry, the Earth forming without water. And later on, once the Earth had an atmosphere, had cooled down and was able to support water, any collisions with asteroids would have brought water to the Earth. And as we saw, they really didn't have to bring that much water to make a big difference in terms of life. So the key point here is that light and heavy hydrogen can tell us that bombardment by asteroids after the Earth formed probably delivered its water. So before we move on, I just want to recap what I've talked about. First, we talked about the nebular hypothesis. We talked about this cloud of gas and dust contracting under its own gravity, forming this protoplanetary disk, this spinning disk of gas and dust. And from those dust grains sticking together to form pebbles, which form boulders, eventually they form planets. Now, we looked at the disk itself. We inspected the temperature in this disk, and we figured out that the Earth was probably too hot initially to retain water. It had to develop an atmosphere first because it was on the wrong side of the ice line. Finally, what we did is we looked at light and heavy hydrogen ratios, and we figured out that Earth's water probably came from asteroids. So Earth had to develop an atmosphere and develop the conditions to keep its water, and then any collisions with asteroids would have continued to bring water to Earth. So on our checklist for building an Earth, where are we? Now we have a planet with liquid water. It's a generic planet, but it does have liquid water, which is very Earth-like. Now Victor's going to tell us about the building blocks of life. And moving on, then Dan will tell us about the uniqueness of life as we know it. So thank you for your attention, and I'll turn it over to Victor now. Thank you.
Awesome. Thank you, Garrett. All right. So, hi, everybody. My name is Victor. As you can see, I got my Zoom outfit on. I got a nice shirt on top and totally not wearing sweats in the bottom. Don't let the sign distract you. I actually do go to Yale. I paid way too much for this being at the bookstore to fake it right now for this talk. So, with that being said, thank you for coming today. I'm going to talk about the building blocks of life. And hopefully this thing clicks. Over, yay. So Garrett just talked about how Earth was formed when asteroids brought water. And to help visualize when this happened on Earth, I made a little timeline for you. And Earth was formed around 4.5 billion years ago. Okay. To put in perspective, the asteroids fell on Earth for about 500 million years. And I kind of made that for you in the bracket right there. And to put this all in perspective, dinosaurs arose about 230 million years ago, and humans were about 2.4 million years ago. So you can see how long ago these asteroids are coming and bringing water to Earth. Now in my talk, what I really want to talk about is where did life come from? That big age-old question of where did life come from? So if we go back on this timeline, I put one more thing on here, and that is when single-cell organisms arose. And that is 4 billion years ago when we first think life happened. And if you look, that's right after water came to Earth. So what is life? Well, life is made of these 4 macromolecules called lipids, carbohydrates, proteins, and nucleic acids. And what are lipids? Well, lipids are things like oils and fats, and these are essential for life. And some of you may be thinking that, oh, I can't be eating fat, Larry, that's bad for you. Well, no, there's good and bad fats. And your cells, every cell in your body, every cell, the outer layer is made out of lipids. And fun fact right now for us living in the age of Corona, the vaccine actually is in a lipid nanodroplet. The little RNA, the vaccine is packaged in a little lipid molecule. And the lipid, because lipid, like your cell membrane, can fuse into your cell and get into your cell easily. So good thing for lipids, because now we got a vaccine and maybe life gets back to normal pretty soon. So the other macromolecule is carbohydrate or carbs. And you get that, and those are sugars. And you get that in the form of bread and fruits and vegetables, or my favorite, the humble potato. I love French fries. And the potato can become so many amazing, delicious things. That's my favorite form of carbs. Now, the other two, protein and nucleic acids, I'm going to explain those a little further. And to do so, we're going to learn about the central dogma. And it's not this kind of dog. I'm sorry. The central dogma is not a little doggy, although I want it to be. What the central dogma is the process of from DNA to RNA to making proteins. And so I'm now going to break down what these processes are. So DNA, what is DNA? A lot of you may have heard it before. And what DNA is simply is the blueprints for life. DNA tells us what makes me, me, and you, you. Everyone's DNA is slightly different, but it really encodes for all of life. All the proteins and everything else in your body, DNA tells you how to make it. Now, RNA. What is RNA? RNA, you can think very simply as a little delivery boy in the body. It takes the DNA and takes it somewhere else in the body to be made into proteins. So the simplest form of RNA, it delivers something. And make sure you tip that very well. And finally, we come across what is a protein. And this is going to be the rest of the talk, really. The building blocks of life are really proteins. And when we think protein, we usually think, right, meat or, meat, chicken, fish, dairy, that kind of stuff. But you can also think of protein as like, oh, wow, I need to start working out again and work on my Photoshop skills, because that could be wow. But you could think of protein, right, as muscles, big, strong muscles like Schwarzenegger right here. And that's protein, right? But that's in the nutritional sense. Now, I want to think about protein more, what is protein really? What's the essence of it? And to help you think about proteins in a simple way, I want to make you think that proteins are like Legos. If you look at structures of Legos, each of those little structures can be a protein. And if you look, some proteins, some of those structures have the same blocks, a little red cube or a yellow or a green. And all of them are unique and different, even if they have some of the same cubes that make them, the same blocks. Well, these little blocks, the individual Legos, those are called amino acids. And these make up proteins. And to help you remember the word amino acid, I have this cute little joke for you. It is, what do you call an acid with an attitude? And this cute little amino acid, and he's saying, give me your lunch, a little mean face on him. And you would call this amino acid. So I hope this little joke helps you remember that word for the rest of this little talk. And now, what are these amino acids? They're not grumpy, right? They make up your body. So what are they? Well, there are 20 amino acids in the body, 20 essential amino acids. And one I want to talk about really is glutamine, because it's very important to me and my work I do here at Yale, and to my family. And so I drew glutamine here for you, and I color-coded every single element in it. And what I really want to point out in this is that most amino acids are made of 4 simple elements: carbon, nitrogen, hydrogen, and oxygen. Those 4 simple elements make up every amino acid in your body. Now, you may be thinking, 20 amino acids, how can it make every protein? There are hundreds and thousands, tens of thousands of proteins that are all unique and different. How can we make so many? We're just 20. Well, if you look at these structures, Or if you even look at something more common, like the alphabet, right? You can see that the alphabet, we have hundreds and thousands of words with 26 letters. Most words that I know aren't more than 15 letters, but most proteins I know are hundreds or thousands of amino acids long. So you can imagine, by having that many possibilities, how many proteins can be made. It's astounding. It's really cool and amazing. And it's all from these simple little building blocks called amino acids. Now, where did they come from? Because if amino acids make proteins and proteins make life, where did amino acids come from? Well, to look at that, answer that question, we're going to go back in time about 4 billion years ago, 4 to 4.5 billion years ago, to primordial Earth. Now, this is an artistic rendition of what maybe it looked like. And there are two things that always jump out at me in this picture. The first is the water, right? This whole talks about the importance of water in life. And you can see the sheer amount of water in this image. But the second thing that always stands out to me are the volcanoes. And the volcanoes and the way in the primordial Earth, scientists would think that these were spewing a lot of gas into the atmosphere. A lot of simple molecules were out there. And also volcanoes, they're hot. They're a source of heat and energy for these reactions to possibly take place. So if we look at Earth's early atmosphere, what we thought it was made of simple gases like methane, hydrogen, or ammonia. And now, if you look at these molecules, you may notice there's something missing. There's no oxygen in them. And if you look back at that molecule I drew, glutamine, there's quite a few oxygens in it. So how is it that life could have been made, but there's no oxygen? Well, two scientists named Miller and Urey back in 1952 took what they thought what the primordial Earth looked like, and they used the resources that were in abundance. They took the simple gases of methane, hydrogen, and ammonia, but they also added one more key element, and that element is water. And you can see in water that could be a source of oxygen. And now the final thing they thought about was primordial Earth might have been a little chaotic and have a lot of lightning. And that's going to be important because in their experiment, this little diagram of their experiment, they put these simple gases in a little glass flask, and they just shot a little electricity, kind of like a spark plug in your car, and zapped it a couple times, and the gases went through, and they got boiled in this water, and that water boiled to the heat source, and that heat source could have been a volcano. And it went through a couple times. And they just did this very simple lightning in a bottle experiment. And this is what they found. They found that at least 5 amino acids were made. The building blocks, those little Legos, were made. Of them was glycine. Pretty simple little molecule that I drew for you. But very interestingly, they also found alpha alanine and beta alanine. And these are both alanine. And they look identical. They're mirror images of one another. But that's in 2-dimensional space. In 3D, they're very different. And that's what Dan's going to talk about next. So I just wanted to give you a heads up in thinking that although these molecules, were made in the same experiment and they're almost the same, they have a unique property. So spoiler alert. Now, looking at this experiment, you maybe think, okay, Victor, that's cool. They made 5 amino acids and pretty simple looking ones, but you need 20 for life. So that can't be how life formed. Well, in the past decade or so, we've looked back and reevaluated what life might have looked like in the back 4 billion years ago. And we did new experiments, and we found that we made actually 17 out of the 20. 17 out of 20. We're getting pretty close now. And we also made the molecules that make DNA. So not only are we making the building blocks, the amino acids to make protein, we're now making the instruction manual to go with the Legos. So you're not just making some random protein, like not even knowing. Now you have instruction in this chaos and disorder world. So to wrap up my talk, I really just want to bring that fact that, we learned how water came to Earth and how this primordial Earth really was the source of, energy, these simple molecules, and these kind of fused together. And simply that proteins, that they're the building blocks of life. And they're composed of amino acids. And we can make this. And we can prove that life could have originated on Earth from this primordial soup, this chaos, this gas. And the final thing I want to leave you with is remember how important water is. That without water, without the source for this reaction to occur and take place, life may not have arisen on Earth. So make sure you take a glass of water next time you see it. Finally, up next, we have Dan, who's going to talk about how these molecules code for life, how we have these alpha and beta alanine, or these molecules that look a mirror image, but how they're very, very unique. Thank you for listening to my talk. Dan, you there?
Yep, just a second.
Cool.
Just a second. Yeah. Hi, so can everyone see my screen? Okay. So I'm the third talk, and I'm going to try to connect the dots and actually try to explain how the biological molecules that formed in the water that we talked about could have actually given rise to life. And I'm also going to talk about molecular handedness, which I'll explain what that is, and why it's very, very important to the origin of life. So a quick recap. Again, we've looked at how water came to Earth. We know it came to Earth through asteroids. Okay. Then Victor told you about how the early Earth may have given rise spontaneously to biological molecules. And I'm going to talk about, of course, how those biological molecules may have also spontaneously given rise to life. So that's the final question here. So let's step back for a second and talk about something that seems completely different. So most objects that you know of in the world have some sort of symmetry, tables, chairs, etc. And most molecules also have symmetry. For example, the water molecule H2O has reflection symmetry, which means that you can take the right half of the molecule and flip it across, and it will look like the left half. That's reflection symmetry. Also, water has what's called rotational symmetry, which means if you take a water molecule and you look at it sort of from the top and you rotate it 180 degrees, it will look the same as it did before the rotation. That's called rotational symmetry. So most objects have some form of symmetry. Now, I'm going to ask you to take a look at your hands. Put them in front of you. I'll give you a couple of seconds to do that. Answer the question, are your hands the same or are they different? So the answer is that they are the same or similar, but they're also different because, and the way you know that they're not, that they're different is that no matter what you do to the right hand, you can never turn it into your left hand, because no matter what you do, your palm will always be facing the wrong way, right? So they're actually different, and that's an important idea. Now take a look at this molecule here. It doesn't matter what atoms this is. It just matters that there's something that's gray bonded to 4 different things. Okay, now take a look at this molecule here on the right, and now answer the related question. Are these 2 molecules the same or are they different? Well, one way you can answer that question is to rotate the molecule on the right to try to make it look like the molecule on the left by aligning all the spheres. So let's do that. Okay, so what do we have? We have an alignment of the purple sphere and the red sphere, but now the green sphere and the white sphere are facing in opposite directions. So as you can see, even though these molecules are mirror images, they are what's called non-superimposable mirror images, because there's no way you can lay one on top of another. And another way to put this is that this molecule has no symmetry at all, just like your hands. So this phenomenon is called molecular chirality, and it comes from the Greek word chieri, which means hand. This phenomenon was discovered by Louis Pasteur, a French scientist. He's famous for also discovering the idea of germs that cause disease, so that's pretty important. But less famous discovery that he made is when he looked into the lees of wine, or the solids that are left behind in a barrel or a bottle of wine. He noticed something interesting. He noticed that there were 2 kinds of crystals, one that looked like the one on the left and one that looked like the one on the right. Now, think about these crystals in the context of what we've just talked about. Are these crystals the same or are they different? Well, the answer is that they're actually different, even though they are mirror images, because again, there's nothing you can do to take the one on the right and turn it into the one on the left, or the other way. And actually now, with modern technology, we know that the molecules that make up these crystals look like this, and they're called tartaric acid, and they are found in grapes and fruit and other things like that. And they have two forms, one that's left-handed and one that's right-handed. Okay, so this is all very interesting, but I started talking about life, and I promised you I'd talk about life, and instead I'm talking about symmetry. Why is this important? Well, let's have a brief history lesson. Let's go back to the 1950s. So 1950s, all of a sudden, a bunch of babies start getting born with missing fingers, arms, legs, and other parts of the body, and nobody knows why. But then they look into it deeply, and they find that a lot of the people who had the babies that were missing different parts of the body had taken a drug called thalidomide before, and this drug is pictured on the right. So what's going on here? So it turns out that thalidomide is a chiral compound, which means it has two mirror image forms, the one on the left and the one on the right, just like your hand. The one on the left actually helps with morning sickness as advertised, but the one on the right causes birth defects, such as missing arms, legs, fingers, and other body parts. So how is that possible? Well, we'll get into that. But the important thing is that any kind of normal process of chemical synthesis where they make drugs in a factory, they'll make 50-50 of the right-handed and the left-handed variety. So if you take a pill of this drug, you'll be getting half of it, half of the drug will be good, and half of the drug will be harmful, just because of a mirror image. Okay, but you might be asking, so why can molecular handedness affect health so much? I mean, they look the same. Why should that actually matter? Well, let's look at our own molecules in our own bodies. So you're familiar with the fact that we have DNA, and you're familiar with the fact that we have proteins, right? Well, DNA and proteins are also chiral compounds that have left and right-handed forms. And it so happens that every single molecule of DNA in your body is of the right-handed form only, and not the left-handed form. And every single molecule of protein in your body is of the left-handed form and not the right-handed form. So understanding this, it makes sense why drugs that have left and right-handed forms can produce different effects on the body, because the analogy is, imagine that you're putting on a glove, and imagine that you have a glove. One second, I'm going to turn off my background. It's okay. So imagine you have a glove, right? And you're putting it on with your right hand, right? That slides in quite nicely, right? But now imagine, try taking a right-handed glove and put it on your left hand. You see, it doesn't work, right? The only way to really put it on completely might actually rip the glove. And that's exactly what happens to the body when you take a drug of the wrong-handedness. So again, the molecules of life are handed, and they generally have only one form and not the other. Okay, but now we're going to get into a sort of a toddler type of cycle where we're constantly asking why. But let's keep asking, because this is really important. But why does this happen? How did this come about? Why do we have DNA that's only right-handed and proteins that are only left-handed? And what does this have to do potentially with the origin of life? Well, back to the Miller-Urey experiment. So this experiment, again, was done in the 1950s, as Victor talked about. And they took simple molecules present on the early Earth, and they mixed that with lightning and heat, and they created amino acids, which are the building blocks of proteins. And then later experiments also created the building blocks of DNA. This is very impressive and actually is super interesting. But Victor didn't tell you one thing. He only hinted at it. That thing is that every single one of those molecules was created in a 50-50 ratio of left and right-handed forms, as opposed to the pure forms that we have in actual life. So this experiment shows how life's molecules could have formed, but it doesn't show why the molecules of life have only one-handedness and not the other. So let's just assume, for the sake of argument, that the reason that a one-handedness dominates in DNA, for example, is because at some point that handedness, the right-handedness, was slightly dominant. There was a little bit more of that kind of molecule. What mechanism could there have been to take that and turn that small difference that could have occurred by chance into a huge difference where pretty much every single molecule of DNA on Earth is right-handed? Well, it could have been a chemical process, and we'll discuss that. It could also have been a physical process that didn't involve any actual chemical reactions or chemical changes, and we'll talk about that. So take DNA. DNA is a molecule that is able to replicate itself, right? So it's a double helix, and the two strands of the helix unwind during replication, and each strand creates a template for smaller molecules to assemble into a new DNA strand next to that strand. And so you can imagine that if the strand in question is right-handed, then the molecules that are going to bind to it are also right-handed. And the way to imagine this is to think of a handshake. Imagine shaking someone's hand with your right hand with a right hand. That's easy and that works very well, right? But what if you tried to shake your right hand with their left hand, or even shake your own hand, right? That's really awkward. So why is it awkward? It's because right goes with right and left goes with left. And the same thing happens with molecules. When molecules like DNA replicate, they make more of their own kind of molecule. And you can imagine that replication from life is actually basically many, many handshakes, each of them happening between two right-handed molecules. So this is what happens when these kinds of molecules divide and replicate. So from 2 molecules of DNA, you get 4. From 4, you get 8. 8, you get 16. From 16, you get 32, and so on. And every time, the amount by which the number of DNA molecules increases also increases, which leads to what's called exponential growth, which you see on the graph here. And you can see that actually, if you have exponential growth, and there's even a tiny difference rate at which right-handed DNA replicates versus left-handed DNA, the right-handed DNA will very, very quickly take off and be very dominant compared to the left-handed DNA. So this is a simple process by which the process of DNA replication could have led to a small imbalance in the right-handed and left-handed varieties, giving rise to a complete dominance of the right-handed variety. So we've established this could have been a chemical process because DNA replication is really a chemical process. Now let's discuss the second option, a physical process. So the physical process that I'm going to talk about is called repeated crystallization. So imagine that on the early Earth, you have these molecules of life, for example, the precursor to DNA or proteins. And you have them in a little small crystals where a bunch of stuff is mixed together, and it's not even just a crystal, it's more like a sludge, right? Now imagine that sludge gets into a pool of water, and that pool of water gradually heats up, and that slowly dissolves some of the compounds, right? And now imagine that this pool of water either evaporates or either evaporates slowly or the temperature goes down. So what that can cause is called crystallization. You can form nice, beautiful crystals. So what happens when you do that is the right-handed molecules find the right-handed molecules, and the left-handed molecules find the left-handed molecules, like a handshake, and they crystallize together. And they make big, pure crystals of right-handed and left-handed molecules. Now imagine that there are 2 crystals, one left-handed, one right-handed, right? And the wind blows and blows the right-handed one into another pool in which some other biological precursor is waiting. And that pool evolves into the first life. But the other crystal, the one that's in this case left-handed DNA, floats away or gets buried, or in other words, disappears. Just by chance, the crystal that created the DNA that we know today, or the template for the DNA that we know today, came from a crystal that randomly blew into a pool of water from one of these repeated crystallization pools. So that's how it could have been a physical process that actually made one-handedness dominant at some point. So now let's just go over where we are. Our DNA is right-handed and only right-handed. Our proteins are left-handed and only left-handed. And we don't yet know why. However, it's clear that understanding the origin of this single-handedness is very similar to understanding the origin of life as a whole. And this is where I come to the quick recap of what we've learned, followed by the conclusion. So again, Garrett talked to us about how water came to Earth. Water is essential for life. Victor talked to us about how the early Earth could have given rise to biological molecules, also essential for life. Now, we've attempted to answer how biological molecules gave rise to life, but I have to say, it's sad, but we actually don't know how that happens because we don't understand where the single-handedness of life came from. But the important thing to remember is that in science, mysteries are really useful. And sometimes asking the right question is much more important than getting the right answer. Because if you ask one slightly better question, you're going to get a lot more, much better answers. And in general, this question of the origin of handedness is one of those questions that will guide origin of life research, hopefully towards some very, very interesting conclusions. Thank you.
Great job, everyone. We have some time for questions now. So we got a couple in the chat during the talks, but if you have a question, you're welcome to, again, type it in the chat or unmute yourself. I'll start with, we had a question in the chat for Garrett. I thought that some rocks and minerals like serpentinite have water in their formulas. It would be fascinating if certain rocks and minerals could only be formed later. After water came to Earth. Is that accurate?
Yeah, so serpentinite specifically is pretty often formed at hydrothermal vents. So where very hot water bubbles up from cracks in the seafloor. So yeah, by definition, there are lots of what we would call hydrated minerals that can actually only form in water, environments with water. So as kind of a tangent, this is actually one of the main lines of evidence pointing towards there being water on Mars in the past, actually, is that even though there's no liquid water on the surface today, we find lots of minerals that could only have formed when water has to have been around. So yeah, that's a really good question. Thanks.
Great. And then I think another one for Garrett. It seems that asteroids bringing water to Earth would have also added a lot of mass in terms of minerals. Is there a way to estimate that?
Yeah, so we can, the best way to do that would be to, I guess, think about this very small sphere of water that I showed in one of the first slides. So in terms of the bulk composition of the Earth, there actually wasn't a huge change because of the asteroids. But there certainly are some minerals and elements such as iridium that would have been brought to the Earth that you otherwise might not expect to be here from asteroids. So yeah, again, yeah, that's a good question. Estimating the mass is a little bit tough, but we can do it. Yeah.
Thanks. Another question that I think anyone can take. How agreed upon is the theory that life formed on Earth? Do any scientists believe in the theory that the first cells/DNA came to Earth from elsewhere on asteroids or comets?
I can talk about this, I guess, since it has to do with space. So yeah, the idea is called panspermia, so life coming from outer space, essentially. While not ruled out, I think that the simplest explanation is probably that life formed on the Earth. I think it's something that hasn't been ruled out, but I think that it would be somewhat unlikely, just given that.
I'll talk more about that too, Garrett.
Yeah, I was going to say if someone wants to jump in here.
They have found like some basic like amino acids on like asteroids, and I think it's from like the energy, like UV radiation could have been like an energy source. But when you think about it, these molecules they need to form somewhere, and water acts like a liquid, like an environment for them to like flow around and interact with each other. And you can't really do that on a flat surface. These molecules don't move, right? So water not only provides the oxygen I talked about, but a safe environment, an aqueous environment where these molecules can go, interact, float around, and be safe. And the water kind of like protects them a little bit. So water, you really need that as well to help stabilize molecules and keep them, originating. And as you heard from Garrett, that doesn't happen in space, right? It's a gas or a solid. So that liquid water on Earth really provides the environment needed.
Great, thank you. A question for Dan. Are there any known metabolic pathways that can convert right-handed molecules into their left-handed versions, or vice versa?
Yeah, so that's a really good question. There are. So while I stressed that, all of our proteins are left-handed and all of our DNA is left-handed, the amino acids that form proteins are occasionally found in their opposite configurations or in their right-handed configuration, because some bacteria, for example, use those amino acids for very special kinds of chemical reactions in their cells. But it's important to note that none of those wrong amino acids are ever used for structure or for actual proteins that do things. They're only used as, for example, poisons to hurt other bacteria or something like that.
Thank you. Another one for Garrett. Did the water have to arrive before an atmosphere formed because it would heat and boil off?
So the water actually has to have arrived after an atmosphere, after there was an atmosphere, because as we were talking about at the position of Earth where it is from the sun, if there was water with no atmosphere, then it would just evaporate away as a gas. It wouldn't really stick to the rocks, and there would be no atmosphere to support it being liquid at the surface. So yeah, there has to have been some sort of an atmosphere, probably not like the one we have today, but there has to have been some gas there to support water existing at the Earth.
Great. And I think another one for you, Garrett. Where did the original dust and gas come from? And why do asteroids contain water?
So the original gas and dust would have just come from you can almost think of it as just from interstellar space, essentially, the space between the stars. Now, what's actually interesting is that stars are essentially big nuclear fusion reactions. And what they do is they convert hydrogen to other elements. So the fact that our solar system has rocks in it means that the material that formed our solar system was actually synthesized in another star that died and exploded, put this material into interstellar space, and there would have, at some point, we were just in the lucky position that there was enough of it to form our solar system. So, and then there was a second part to that question, I think.
Why do asteroids contain water?
Okay. So asteroids just happen to form in the solar system past the ice line. Actually, they formed right around the ice line, but enough of them formed in a location where they could have just incorporated water that happened to be in the gas and dust. So.
And another question about the atmosphere. Since we watch things burn up on reentry, would the water enter the atmosphere and not make it to the surface?
It depends how big your rock is, essentially. So if you have very small, if you have small asteroids, then they probably wouldn't make it to the surface. Now they could still deposit their water. It would just, yeah, I mean, they would just break up into smaller bits, and and some of that water would still make it. But it does help to have larger rocks. Essentially, they have a much better chance of making it to the surface.
Right. So if they were, even if the asteroid broke up in the atmosphere, the material it was made of is still captured by
the
Earth.
The material should still be there. Yeah.
Mm-hmm. Yeah, and so those are all the questions I had stored up. But please, feel free to ask in the chat or unmute yourself if you have something else.
I'm just gonna give a shout out to my friends for coming tonight. Thank you guys. You're amazing. I love you guys. Thanks for the support.
No problem.
And my parents are actually in the audience, so I wanted to say thank you for coming as well.
Can I unmute and ask a question?
Yeah, absolutely.
So is the handedness, quote unquote, of these things like those artificial sugars that they put into food so that your body can't absorb it, but you still think it's sweet? Is that handedness thing?
So that could be something you can do. So I think it so happens that the sugars that aren't absorbed by the body, they aren't absorbed by the body not because they're simply the wrong-handedness. There's something else chemically about them that the body doesn't recognize. But in theory, if, for example, a wrong-handed version of a molecule was sweet, but but wasn't absorbed, they could use it as a fake sugar. But actually, something that's really interesting is that sometimes molecules that look the same but have opposite handedness have different taste and smell. So, for example, I think the compounds that make up certain essential oils, like caraway and I forgot the other one. Basically, the two molecules are just opposite handed versions of the same thing. So it's unlikely that something that is an inverted sort of sugar would actually taste the same as sugar.
Actually, I have a question. So we know like our DNA and also the protein there all have a certain handedness. I'm just curious, is there any particular reason like during the evolution that they all went to that certain kind of handedness?
Yeah, so that's sort of some of the things that I wrestled with in the talk, and I wrestled with these things, but we didn't get to any definite conclusion because nobody knows. But one compelling idea is, imagine life evolved exactly once. Let's say that happened. It's such a rare event that it happened once. In that case, it's easier to understand how maybe the crystals of some of the molecules that formed that early, life-producing soup had one-handedness and not the other simply by chance. And that would sort of make sense considering that our nucleic acids or DNA and our proteins actually have opposite handedness and nobody knows why. But the real answer is that nobody knows. But the cool thing is that trying to understand this is really the same as trying to understand the fundamental origin of life, which is, a good question.
Thank you.
Mm-hmm.
Okay, if there are no more questions, I would just like to thank all of you so much for these really wonderful presentations. And I don't know if you saw in the comments, but there were a lot of people who are voicing the same sentiment. They thank you for this and that it was really interesting, really fascinating to hear about your research. And thank you for presenting this to our library.
Oh, that's fantastic. Thank you so much for having us.
Of course.
Thank you so much, Rachel.
Thank you. And there'll be one more presentation, I believe in April, with this series through the Brookfield Library. And so I hope everyone will tune in again. And we did record this presentation, so it'll be available on the YouTube page for the Brookfield Library if anyone's interested in sharing it with others. So again, thank you so much.
Fantastic.
Thank you.
Bye.
Have a good night.